Hi everyone, welcome back to Chem Help ASAP. Today we're going to be calculating equilibrium concentrations and pressures, and we're going to be doing this using ice tables. Let's get started. So first we need to know what an ice table is. And really, it's just a way to help us organize information so we can calculate our equilibrium concentrations or our equilibrium pressures. So ICE is an acronym. Let's go through what each letter stands for. I is for your initial concentration or your initial pressure. C is for either consumed, or some people think of this as change. And E is for equilibrium. So let's work through a problem using an ICE table. So we have a reaction right here that is in equilibrium. At 25 degrees C, the KEQ of this reaction is 0.90. If a 1 liter flask is initially charged with 2 moles of carbon monoxide and water, what are the equilibrium concentrations of all species? The first thing we need to do is we need to get our initial concentrations, or the I part of our ICE table. Now, this problem gives us how many moles we have, and it gives us a volume, so we can calculate molarity. So let's calculate our molarity of carbon monoxide. This is going to be 2 moles of carbon monoxide divided by 1 liter. This is a very simple calculation, so we have 2 molar carbon monoxide. The same is true for water. We have 2 moles of water and 1 liter, so we have a 2 molar concentration of water as well. Okay, let's start filling in our ICE table. You'll notice I put my acronym in this first column here. Again, this is going to be initial concentration. This is going to be how much is consumed or a change, and this is equilibrium. We just calculated our initial concentrations of our reactant, so I'm going to go ahead and put those in right here and here. Now, how much of our product do we have? Well, our problem tells us that we only have carbon monoxide and water. So we assume we have no product to start with. This is just an initial condition. So I'm going to put a 0 in for hydrogen and a 0 in for carbon dioxide. The next piece I need to fill in is my C for my consumed or my change. To do this, we need to know which way the equilibrium is going to shift. Now, this problem is quite simple. We have reactants only, we have no products, so our reaction is most definitely going to shift to the right to form products. That means I am going to consume some of my water and my carbon monoxide to form hydrogen and carbon dioxide. Now, I don't know how much this is going to change, so I'm going to call this X. So I'm going to have minus X both in my water and my carbon monoxide boxes. And specifically, these are minus 1x because there is a 1 in front for our stoichiometric coefficients. Again, I know these are minus x because we are going to consume some of our reactants to form products. Now on the product side, I know I'm going to form products. Again, I don't know how much, so I still call this x, but these are both positive x because I am going to form some of my products. Again, this is why some people like to think of this as change instead of consumed, because over here our x does not stand for what is consumed, but what is actually formed. Use whichever term makes the most sense to you. Again, these are both 1x because there are 1s in front of my hydrogen and my carbon dioxide in my balanced chemical equation. Now it's time to fill in the E part, or the equilibrium. This is going to be my equilibrium concentration. And I simply add down the column. So my equilibrium concentration of water is 2 minus X. The same is true for my carbon monoxide, that's just 2 minus X. And for my hydrogen and carbon dioxide, these are both X, although technically they are 0 plus X on both sides, which is just easier to write as X. Now that our ICE table is filled out and we have expressions for our equilibrium concentrations of both our reactants and our products, we can use our KEQ to calculate what X is. We're definitely going to need some more space though, so let's go to the next slide. Okay, so I'm keeping my ICE table right here at the top to reference because I am going to need specifically this equilibrium row right here. Let's write the KEQ for this reaction. Remember, KEQ is products over reactants. The nice thing about this reaction is everything is 1-to-1, so I'm raising everything to the first power. Remember, when we're writing our KEQ, these must be our equilibrium concentrations of our products and reactants, which our ICE table actually specifies. So I'm going to take each of these expressions and I'm going to plug it into their appropriate place. I also know the value of my KEQ. The problem gave it to me. So I'm going to put that number in as well. Okay, so this is what our expression now looks like. We have 0.9 substituted in for our KEQ. Our equilibrium concentrations of hydrogen and carbon dioxide are each X. And of course, our equilibrium concentrations of water and carbon monoxide are 2 minus X. This is purely just a simple substitution. Now we need to get into some algebra. So I'm going to simplify these expressions. X times X gives me X squared. 2 minus X times 2 minus X gives me 2 minus X squared. So I can take the square root of both sides of this equation. That gives me 0.949 equals X over 2 minus X. Again, we're just working through our algebra here. So we need to take this quantity over to the left-hand side of the equation, like so. We're going to distribute this 0.949. Here is our expression here. Now we're just going to combine like terms, and we get X equals 0.974. Now let's remember what X is. Remember, we set X up to be our consumed or our changed. But the problem wanted us to calculate our equilibrium concentrations of our reactants and products. Well, let's start with the easiest. Let's start with our products, because our equilibrium concentrations of both hydrogen and carbon monoxide are the value of X. So our concentration of hydrogen is equal to our concentration of carbon dioxide, which equals X, which we just found, which is 0.974 molar. Now let's talk about our reactants. Remember, we have an expression for our concentrations of reactants. Again, our water and our carbon monoxide are the same. They both equal 2 minus X. So just straight up plugging X in here, we get our equilibrium concentrations of water and carbon monoxide equal 1.03 molar. But usually for ICE tables, I find that one example is not quite enough. So let's do another example. Okay, so we have a new reaction. Hydrogen and chlorine gas go to form hydrochloric acid. The problem reads, at 350 K, the KEQ of this reaction is 1.25. Initially, 1 mole of hydrogen and 2 moles of chlorine are placed in a 1-liter flask. How many moles of hydrogen, chlorine, and hydrochloric acid are present at equilibrium? We have an initial amount. We're trying to find equilibrium amounts, so we want to use an ICE table. Here is our ICE table. We need to fill in what we know. Remember, I stands for what we have initially. In this case, we are working with concentration. So what is our initial concentration of hydrogen gas? Well, we have 1 mole, and that is in a 1-liter flask. Remember, molarity equals moles over liters. So in this case, this is 1 mole of hydrogen in a 1-liter flask. So our concentration of hydrogen is 1 molar. It's just as easy with chlorine. We have 2 moles in a 1-liter flask. I won't bore you with the calculation. That is a concentration of 2 molar. This is an initial condition. We have put hydrogen and chlorine in the flask, and we are allowing this to come to equilibrium. So our initial concentration of hydrochloric acid is going to be 0. The next row of our ICE table is C, again for consumed or change. So which way is our equilibrium going to shift in this case? Well, because we have 0 product, our equilibrium is definitely going to be shifting to the right to make products. But again, we don't know how much. So I am going to call this quantity X. Now, on the reactant side, this is going to be minus X and minus X because we are going to consume some of our reactants to form products. And on our product side, we are going to have 2X. Now, you might be wondering why we have a 2 here, and that is because of the stoichiometry. There is a 2 right here in front of our hydrochloric acid. This is a positive 2X because we are forming product. Okay, so now we can fill in our row for equilibrium. Again, we're just going to add our initial and our change. So our equilibrium concentration of hydrogen is 1 minus X, of chlorine is 2 minus X, and our hydrochloric acid is just 2X. Or again, it really is 0 plus 2X, but we can just write this as 2X. Now that our ice table is filled in, we need to get our expression for KEQ. Again, products over reactants. Here is our KEQ. Remember to square your hydrochloric acid because it has a 2 in front of it. And now I'm going to plug in for all of my concentrations based on my ice table right here. Okay, so I have a value for KEQ, that is 1.25. My concentration of hydrochloric acid is 2X. Again, don't forget the square. That's kind of a common mistake I see. And for my reactants, my hydrogen is 1 minus X and my chlorine is 2 minus X. All right, so our math is going to get a little bit messier here. Let's give ourselves a little more space. Let's go to the next page. Okay, so again, I'm just going to keep my ice table up and also my expression for KEQ. We have already done this part, but we'll need to reference it. For this calculation, because my denominator has 2 different quantities, I can't take the square root of both sides. That's not going to help me any. So I'm going to have to FOIL my denominator to get a quadratic. Okay, so my numerator does simplify to 4x squared, and here is my denominator right here. In order to solve this quadratic, we need to set it equal to 0. So we're going to, again, need to do some algebra to get it set equal to 0, and then we can use quadratic equation. So I'm going to take this quantity over to the left-hand side, just like so. I'm going to have to distribute this 1.25 across this whole quadratic. Here we go right here. This is still equaling to 4x squared. At this point, I need to combine like terms. And once I bring this 4x over, then that will set it equal to 0. So here is my quadratic set equal to 0, which means I can now use the quadratic equation. You can solve this quadratic by hand. Me personally, I like to use the quadratic program that I have saved in my calculator. So when I run my quadratic program, of course, I get 2 values for x because this is a quadratic. My x can equal either 0.490 or negative 1.85. So which value do I use? Well, I definitely want to use the positive value. If I use the negative value for x, that is going to give me a negative value for my concentration of hydrochloric acid. That is not possible in chemistry. So whenever you get a negative answer for x, you know you can drop that one. So my value for x is 0.490. Okay, hang in there, we're almost done. We need to still get equilibrium concentrations. Let's start with the hydrochloric acid. Of course, our concentration of hydrochloric acid is just 2 times x. So that's going to be 2 times 0.490, and that is 0.980 molar. For hydrogen, that is going to be 1 minus x, or 1 minus 0.490, and that gives us 0.51 molar. And finally, for our chlorine gas, that is going to be 2 minus x, or 2 minus 0.490, and that gives us a concentration of 1.51 molar. I definitely recommend getting that quadratic equation program in your calculator if you don't have it already. Okay, let's do another problem. New reaction. Carbon monoxide plus chlorine gas goes to COCl2. At 500 K, the KEQ of this reaction is 2.7 times 10 to the negative fifth. If a 1.5 liter flask is initially charged with 3.75 moles of carbon monoxide and 2.63 moles of chlorine, what are the equilibrium concentrations of all species? Okay, so you know the deal here. Let's set up our ice table. All right, so here is our ice table. Of course, we need to start with our initial concentration of everything, which we do not have quite yet, but we know our moles and we know how big our flask is. Now, unfortunately, our flask is not a 1 liter flask, so we're going to have to do just a little bit of math to get those initial concentrations. So for carbon monoxide, we've got 3.75 moles divided by 1.5 liters, and that gives me a 2.5 molar concentration for carbon monoxide. Chlorine gas is going to be 2.63 moles over 1.5, which gives me 1.75 molar for my initial concentration for chlorine. Okay, so let's go ahead and get those numbers in. Here we go. We've got 2.5 and 1.75. Again, how much product do we initially have? Initially, we have none because we have only put carbon monoxide and chlorine gas into this flask, so I'll put a big 0 right here. Okay, next row, C, consume or change. Again, we know we're going to shift to products. So this is going to be a minus x, and this is going to be positive over here. Again, we have ones in front of all of our x's because we have ones in front of all of our species in our balanced chemical equation. Okay, now to get our equilibrium row, again, we're just going to add our initial and our consumed, and we get 2.5 minus x, 1.75 minus x, and then of course just x over here. Ice table is now done. Let's get our expression for KEQ. Okay, so KEQ, again, just products over reactants. This is a little simpler. Nothing is raised to a power here, so that helps. Let's plug in for our KEQ because we have that number from our problem, and also we have our ice table to give us our equilibrium expressions. So we have 2.7 times 10 to the negative fifth. We're going to have x over 2.5 minus x and 1.75 minus x. Again, we've got some algebra to get through, so let's switch over to the next page, give ourselves a little bit of space. Still keeping my ice table up and my expression for KEQ plus the one with all the numbers in it. Okay, this is actually a special case. We're going to get a little bit of help with our quadratic. When our KEQ is very small, it means that this reaction heavily favors reactants. Or in other words, you can think of this as the change in concentration of our reactants is not going to be very large. So how does this help us mathematically? Well, we're going to assume that x is very small. And what that means mathematically is that 2.5 minus x is approximately equal to 2.5. And the same is true for our 1.75 minus x. That is going to be approximately 1.75. This is going to simplify our denominator tremendously. We can drop these minus x terms. Now, usually we can drop these minus x terms when our KEQ has an exponent of 10 to the negative third or smaller. But when we're done with our calculations, I will show you how to check this assumption. Okay, so let's move forward assuming that x is very small. So our KEQ simplifies to this. So in the denominator now, we just have 2.5 times 1.75. That's so much easier than having two quantities that we're going to need to FOIL. So we multiply our denominator, and this is just a really simple solve for x. We don't even have to solve a quadratic. So our value for x is 1.18 times 10 to the negative fourth. It is very, very, very small, just like we assumed up here. Now that we know x, we can get our equilibrium concentrations. So let's start with our easiest ones, our COCl2. Of course, that just is the value of x. So our concentration of our product is 1.18 times 10 to the negative fourth. We have our concentration of carbon monoxide. This is 2.5 minus x, which is 2.5 minus 1.18 times 10 to the negative fourth, which is just 2.50. Remember, this is 10 to the negative fourth. We would have to put a lot more sig figs in here to start to see a difference. The same is true for our chlorine. This is 1.75 minus x, which is 1.75 minus 1.18 times 10 to the negative fourth, which is still just 1.75 molar. Again, we would have to have a tremendous number of significant figures before we could actually see a difference in that concentration, which again matches with our assumption that our 2.5 minus x was 2.5 and our 1.75 minus x was our 1.75. So things are looking good for our assumptions. But we can actually test this with something called the 5% rule. So our 5% rule states that x over our initial concentration of carbon monoxide times 100% should be less than 5%. If it is less than 5%, then our assumption is good. Okay, so the same thing is true for our chlorine here. Again, our value of x over our initial concentration of chlorine times 100% should be less than 5%. So let's put these numbers in. So our value for x, of course, is 1.18 times 10 to the negative fourth divided by 2.5 times 100%, and we get 0.005%. Yes, that is definitely less than 5%. Let's check for chlorine. Again, here's our value for x. This time we're going to divide by 1.75, multiply by 100%, and we get 0.007%. Yes, less than 5%. Again, we can use this simplification when our KEQ is small, and the general rule of thumb is when you have a KEQ that's 10 to the negative third or smaller. Okay, so that's how to deal with an ice table when you have a small KEQ, but let's see an example with a little bit of a twist. We have a new reaction here. Our problem reads, initially 2 moles of NaCl and 1.35 moles of chlorine are placed in a 1 liter flask. At equilibrium, the concentration of chlorine was found to be 1.58 molar. What is the KEQ of this reaction? So in our previous problems, we have been given the KEQ and asked to calculate equilibrium concentrations. In this problem, we're asked to find the KEQ, but we only have one equilibrium concentration. So this is not just a simple calculate KEQ from all our equilibrium concentrations. We've got some initial concentrations and one equilibrium concentration. Okay, so here is, of course, our ice table. Let's fill in what we know. So again, let's start with initial conditions. At least for calculating this concentration, we're in a 1 liter flask, so our 2 moles and our 1.35 moles are just going to go straight to molarity. So we have a 2 molar concentration for NaCl, and we have a 1.35 molar concentration for our chlorine gas. Now, we don't have any of our nitrogen monoxide. So again, a little bit different from the problems we have seen. However, it does still mean that our reaction is going to shift to products because we have a 0 here on our product side, and it doesn't matter that we have a little bit of another product. At equilibrium, we're going to have some of all species. All right, so now that we have our initial concentrations, we need to do our change. Again, we know we are going to form products because we need to form at least a little bit of our nitrogen monoxide. So this is minus 2x. This becomes positive 2x, and of course this one is also positive x. We're going to shift to the right. And just as a reminder, we have a 2 here because in our balanced chemical equation, that is a 2, and the same is true for our nitrogen monoxide. Of course, our x here is just a 1x because there's a 1 in front of the chlorine. Just yet another reason to make sure that any chemical equation you're working with must be balanced. Our equilibrium concentration for our NaCl is 2 minus 2x. For our nitrogen monoxide is just simply 2x, and then for our chlorine is 1.35 plus x. So a little more complex in our equilibrium row. Let's get our expression for KEQ. Again, products over reactants. Here we go right here. Don't forget your 2 squareds because again, we have 2's in the balanced chemical equation. So plugging in from our equilibrium row, this is our expression for KEQ. Again, we're going to need more space, so let's switch over to a new slide. Here we go, but still keeping our ice table and our KEQ expressions right here. Okay, at this point, we have a problem. We do not know our KEQ, and we do not know our value for x. We cannot solve if we have one equation and 2 variables. So there must be a way to eliminate one of these variables. So we are actually going to find the value of x by using our equilibrium concentration of chlorine. So remember, back in our original problem, let's go back. If we look at our original problem, we know that at equilibrium, the concentration of chlorine was found to be 1.58. This is our piece of information we need to eliminate one of our variables so we can solve for KEQ. Okay, so our equilibrium concentration of chlorine is our 1.58 molar, but that equals our 1.35 plus x. Again, I'm just pulling from my ice table. I can solve this expression for x, and I get x equals to 0.23. So now that I know my value for x, I can plug in for x in my KEQ expression, and that will give me a value for KEQ. Okay, so it's going to get just a little bit messy, but again, we're not having to solve it a quadratic, so that's a good thing. So I have 2 times x squared, a 1.35 plus x, and a 2 minus 2 times x squared. Just watch your algebra when you're doing these calculations. So let's just simplify a little bit. Here we go. We've got a 0.46 squared times a 1.58 over a 1.54 again squared. Simplifying again, so I just have a numerator and denominator. Finally, I get a KEQ of 0.14. As you can see, your ice table calculations can get pretty hairy pretty fast. The most common thing I see is that students kind of get lost in the algebra and lose sight of especially what does X mean? When you've solved for X, what have you solved for? So yes, you are going to have to wade through the math, but keep the chemistry in mind as well. I hope you found this video helpful, and thanks so much for watching.